notably, in the rest of this talk, I'm going to assume that x is moving faster than y. So mu x here is 1, and mu y here is 0.1. That means in one generation, species x actually hops 1 times in average. And in 10 generations, species y actually hops 1 times. So these are the traditional, a typical simple path that you will see. And so from the point of view of statistical physics, what we can do is to prepare identical samples. By identical, I mean you prepare the system with the identical initial condition, and you let it evolve. You see how the probability distribution evolves. So here, to the left-hand side, I'm going to show you a system where the population scale is around 500. Here is a population scale around 200. The environmental distribution is roughly the same. So you'll see very similar green dots. But what you can see in the simulation is actually you see some kind of suppressed motion where you never see these dots actually moving far away from this channel. So that actually gives us some clue. And secondarily, what we observe is that the extinction events here, when the population scale is small, is actually it happens much earlier than when the population scale is higher here. All right. So for example, like right now, you see a bunch of the system actually has extinction of y, a bunch of system extinction of x, and then you measure how many of these divided by the total sample path you prepare, then it's going to give you some number like 53% of the time species X wins, etc. And then we can sort of measure the advantage of being fast or slow. How about heterogeneous many patch model? We use roughly the same idea, but right now the random variable, suppose we have n patches, then there are two n-dimensional. It's a 2n-dimensional system because we right now have a 2n random variables. Once again, I'm going to project it onto 2-dimensional phase plane, and I'm going to visualize only one single realization. That means there's only one. I only run the system one time. But since the system itself actually has many patches, so as you can imagine, there are a lot of green dots, and at the end, if you have enough, then you see more like a green band. And so I plot population x1, y1, x2, y2, xi, yi, etc. If you plot them all together, and in this mean field model, what you would expect is that it's a mean field. So I don't have to run many realizations. What I have to do is to just one realization, and all these stochastic processes on different patches is going to give you some kind of average result. But surprisingly, this is what you see. Once again, left-hand side is a population density, overall population density per patch. Sorry, population scale per patch is around 500, and right-hand side is around 200. So this is what you see. Species X is actually moving faster than the species Y. And here T is actually generations, roughly the generation. So after about 1,000 generations, what you see is the population of species X declines in this regime when the population scale is high, but increase in this regime. So this is the regime shift that I show you in Kessler and Sanders results. So what happens in this system? Actually, stochasticity is responsible for this. Okay. Due to the time limitation, what I'm going to show you is walk you through our derivation, which might be dry in the sense that it's, I won't say hard, very tedious, but I'm going to only talk about two-patch model so that I can actually list all the equations. The mean field model is actually you can actually use the same concept to compute the mean field model, but I chose to use a two-patch model. So here you write down the master equation. Anyone who learns stochastic processes should be able to actually write this down, where here P A B C D is the probability of a state being x1, y1, x2, y2 is equal to A, B, C, and D. The left-hand side is a physical time. The change of a probability is equal to the sum of these probabilities with certain states. And the idea actually here is to say when my population scale here is large, this lambda is large but finite. Mathematically, what do I mean by large but finite? If you ever took asymptotic analysis or learned WKB from Professor Chen, he'll show you that large means that this lambda is probably greater than or equal to 3.5. It's large enough. Then what we do is to expand this 1 over lambda in this equation, and then by Taylor series expansion, there's a theorem tells you that you can expand 2 orders and then obtain this Fokker-Planck approximation. From the previous slides to here, it's called system size approximation, or sometimes people call it system size expansion, sometimes people call it Van Kempen expansion, but we can do that. And there are theorems proven to show you that this is a safe way to actually do this. And then in the Fokker-Planck approximation, the probability becomes, the time here is scaled from S to T, and the probability P becomes a joint probability distribution. And you'll see I put a K here. It's going to be the harmonic mean of the carrying capacity. It's just the mean carrying capacity. It's a scale of the total population per patch of the system. And the Fokker-Planck equation consists of 2 different terms, one of which is the first derivative. It's like a advection field of the joint probability distribution. It shows how this probability distribution actually flows. And here you see a doubly differentiation. These terms are actually the diffusive field of the joint probability distribution. So we actually, Heijin and I actually stare at this equation, and then after a year or so, we decided to just give up because it's hopeless to actually solve this. So there's a theorem though that suppose we look at this K here. This K is a population scale. So suppose you send this K to infinity. There's a mathematical theorem shows you that the dynamics when K goes to infinity converges to the dynamics of this equation. It might be a little bit strange to actually state this to physicists, but there's a theorem actually there proving that you can actually do this safely. And so look at this equation. This is actually something we have to learn in probably statistical physics, in the sense that this is actually a Liouville equation. It's a Liouville flow. So this is a probability distribution, and then these are the flow of how this distribution should flow. And the entire Liouville equation actually tells you only one thing, is that if you prepare the system by a delta function, suppose your probability distribution is a delta function, then it evolves like a delta function. It never disperses. So what does that mean? This is actually how physicists can help mathematicians. So I told Charlie and Heijin, why don't we just look at the Liouville equation, and then before we actually solve the entire equation, the entire Fokker-Planck, let's just look at this and then see how it moves. So this is what this moves. Suppose I have no hopping events. That is mu x is equal to 0 and mu y is equal to 0. Then you know the entire system becomes a isolated patches. So we know how to solve this equation. Actually, these are just two isolated logistic dynamics, and then we know the trajectory should look like this. So starting from any initial condition, it just converge to its own carrying capacity. That's it. So what happens if we turn on the hopping in a symmetrical way? Say mu x is equal to mu y is equal to 1. Then you're turning on the chemical potential. That is to say, you want to shorten the distance between this red and this blue. So you don't see this separation of red here and blue here, for example, like this. There is certain kinds of attraction force trying to attract these 2 points so that they are near to each other. But in this very special case, when mu x is equal to mu y, then again, you don't see distinguishable species. You see x is just y. So at the end, they sort of, you know how they are actually, they stabilize to a certain consistent state. All right, so what happens if we turn on this dispersional events in an asymmetrical way? This is what we see in the system, is that very fast, in a very fast time, the system sort of still is pushed or pulled by the logistic dynamics, so that it converges to inside this channel. And then, nevertheless, because there's a difference between them, mathematically you can compute using perturbation theory, asymptotic analysis, whatever. You can see that you can prove that there is a slow drifting field in mathematics. It's called the center manifold of the system. There exists a center manifold, so that in a very short time, it converges to the center manifold and then stay there, and then move toward to a certain direction slowly. So now it's actually one of my favorite kind of feature in dynamical system. That means that you have a separation of time scale of a system. So what you can do is actually, there are a lot of tricks you can do for a system which has a separation of time scales. But I'm going to show you how we actually utilize this later. But I want you to actually remember that maybe in the future you see some kind of a system like this, then there are good tricks that we can do. All right, so once again, as a physicist, we're compelled to throw a lot of random initialized systems on the phase space and then see how they evolve. So I'm going to show you a randomly initialized system. Within a very short time, that is several generations, all the states are being absorbed into the center manifold. And what I would like to say a bit more is actually you can see the velocity field on the center manifold. It's actually not uniform. So here, things are moving quite fast, rather than here, things are mostly just stable. So using traditional asymptotic analysis, what we can do is to calculate and characterize this velocity field here. So we know part of the story. When the population scale is infinity, we know what happens. Now what happens when we talk about stochastic system? That is this equation. Then this is what we figure out at the end when we couldn't solve this equation. What we say is, since we're considering large k, that is, once again, what is large? It's just 5, 10, or maybe 20 is super large. Then these term becomes negligible to the advective terms. So when far away from the center manifold, we simulate the system, or we imagine the system only evolves according to the advection field. And these golden terms is going to be the dominating factor. And this red term is going to be dominated by this golden term, and then we just ignore it. Nevertheless, when when it is near to the center manifold, these terms are going to be small due to critical slowdown. Critical slowdown is just the motion that I show you, that when it converges to the center manifold, it becomes very small, slow, so these terms are going to be small. And that is when these terms comes into play, then we have to consider this term. And then in that regime, what we say is, we don't care about these golden terms. We only care about the red terms. So at the end, this is what we develop, is a system where a possible, okay. So this is our approach that I make a cartoon so that it is actually easier to visualize. So suppose this is my slow manifold, and suppose this is my state vector, which is denoted by a red dot. And when it is far away from the center manifold, it more or less just flow along the deterministic trajectory onto the center manifold and stay there for a long time. But we don't forget that when it is near here, it is dominated by the diffusive process. So one red dot is going to be scattered out by the diffusive process, and then we use only 2 red dots to actually characterize such a diffusion. And suppose you have many different fluctuation, different direction of fluctuation, you use some other directionality from a stochastic differential equation we derived, and then use a linear superposition. And then since it is far away from, sorry for the sound. So when it's far away from the center manifold, it is again flow along the deterministic trajectory back to the slow manifold. And then we set up a effective coordinate z here. That is initially where the red dot is. It's right here. And we set here is when z is equal to 0. And then you measure all the z's of these dots. And then you measure the effective drift, z, average all this z1, z2, z3, z4 to z whatever. Actually, in this system, there are actually 64 different z's. And then as well as the effective diffusion constant. And then you can write down that one-dimensional effective stochastic process on this slow manifold. And then what we do is to use that effective dynamics to predict the system. And let me remind you one thing. So remember the first animation that I showed you, all this fluctuating population? What we do here is actually using 2 consecutive processes, scattering out, converging, scattering out, converges back in. And it's quite different from what we actually see in the simulation. Nevertheless, after the computation, what we can show is that on the center manifold, there exists 2 different terms, one of which is due to the deterministic motion, which is proportional to sigma squared. The other is proportional to, the other is due to stochasticity, which is proportional to 1 over k. And let me remind you one more time, this is a population scale. So when the population scale is high, this term is low, this term is small. And this is a tug of war. And depending on which one actually wins the competition, you can drive the system toward this end or the other end. So a reasonable guess is actually when you divide this term by that term, then you get a sort of a non-dimensionalized scale, which should be proportional to k sigma squared. And this k sigma squared is actually the boundary of the regime shift proposed by Leonard Sender and David Gaslight. All right, I'm going to skip the equation, but to show you just we can identify 2 different terms, and there is a key control parameter of a bifurcation, and in the mean field model, it takes a similar form. And these are the results of our simulations. The solid line is our prediction. And you can predict the winning probability of x as a function of the initial distribution of the system. So when z0 is equal to 1, that means 100% of the time sorry, initially the population is 100% of species X, so Y has no chance to win. So it's going to be with probability 1, species X wins. On the other hand, when it is equal to -1, that means that 100% of the initial population is species Y. And then with all these discrete markers are actually from continuous time Markov chain simulation, and as you can see that it agrees pretty well, as well as the mean extinction time. Right. And it's a large-scale validation of our theory. And for the mean field model, we actually monitor the average population as a function of time of species X and Y. I don't have time to actually talk each of the curve, but as you can see that our prediction, which is a solid line, explains what happens for the discrete marker, which is the simulations quite remarkably well. All right. So then we can actually predict the regime shift where the fast wing, this is a reproduction of David Kessler and Leonard Sanders. And what we can also do is to predict the bifurcation. Since it's a Taka 4, you can actually have a certain, in some parameter regime, the velocity field is always positive, which drive the system always toward to the right. And some of the times it's always blue, so it's always driving to the system to the left, which is Y dominating. But what is more interesting, you can have some green, which there's an intersection. So driving the system to the right when it is in this region, and driving the system to the left when it is in this region. So you can see a coexistence state, as well as, and this is a stable coexistence state. You can see an unstable coexistence state, etc. But what is more interesting is we can actually put a bifurcation diagram, which is ecologically sensible. What does that mean? Is that when that control parameter is small, that is when the population scale is small, or when the environmental variance is small, then you plot mu x versus mu y, and then you denote x wings by here, and y wings by blue. So that means that I want to be fast, right? Because being fast wins the competition. But when you increase that control parameter, what happens is that you start to see one unstable fixed point, and then you increase it furthermore, then it reverse, where you want to be slow in this region, because here mu x is greater than mu y, but y wins. What is more interesting is that after a certain point, there is a bifurcation. So the entire system looks like this. You see one stable fixed point. You see a pair of stable, unstable fixed point. More or less, if I am species X, I want to choose this mu x, because regardless of what mu y is, I always win. So this is in mathematical biology. We try to find this wedge-like pattern where this state is going to be evolutionarily stable for species X because I always win. Then I should choose this. Right? Similarly, because of the symmetry of the model, for Y, I want to choose this rate. And any perturbation near this state is going to be driven by the dynamics back to the states. So this is actually what we should see to be the most stable dispersion rate. All right, and further increasing that control parameter, decrease this evolutionary stable rates down to 0, which converges to the traditional ODE or PD theorem. All right, let me fast forward the conclusions and wrap up. So now we know the selection of a regime shift. There's an outcome of the following effects. The first is nonlinear deterministic dynamics, which establishes slow manifold. And this actually favors the slow dispersion. And the time scale of it is actually inverse to the environmental variance. And the stochastic perturbation near the slow manifold actually contributes to an effective drift, which favors the fast dispersion. And time scale is actually proportional to the population scale. And depending on which time scale is actually larger, it is actually, you can predict which one wins. And we know the closed form, we know the outcome, and we identify a control parameter, as well as a regime shift and bifurcation. And what is more interesting is that we can prove the existence of the evolutionary stable dispersion rates. In addition, we predict that the faster dispersion always have the advantage. Nevertheless, this is actually in our computation. It shows up to be a very weak effect in the sense that it shows up in the second order of the perturbation theory. So what that means is actually the common rationale is not correct. We actually can show a counterexample that by changing the death rate from this form to the other form, actually people use this form to model real system. And when this lambda is large enough, you can actually see that the velocity field is flipped. And originally it's trying to drive the system toward to the right, but in this when lambda is large enough, you see in the majority domain, they actually drive the system toward to the left. And in simulation, what we observe, this is our prediction, and in simulation, what we can actually show is that they actually change the advantage of being fast. So what happens to the common rationale that you want to move fast so that you can locate the unused habitat? The reason is actually these are passive dispersions. So of course you can move fast to actually get into the spot more quickly. But if you are being fast and then you have an impulsion to actually leave at some established habitat more frequently. So to the first order, you're leaving your established habitat more frequently, but you're getting unused habitat more frequently, so they balance off. Okay. And what is left to say is actually that this is a second order effect, and it's not that intuitive. You can actually tweak the model a bit, and then see totally different conclusion. All right, to me, what is more interesting is actually in this dynamical system, you can see some noise-driven resistance. So this is one of the system in many-patch model that prepared the system in 3 distinct initial conditions. And in mathematical biology, there's a famous theorem called the mutual exclusion principle that it says that if you wait long enough, only one species, only one phenotype can actually win. But this is actually driven by the noise, the demographic fluctuation. Try to stabilize the system to a certain coexistence of about 80% of the population is X and 20% of the population is Y. And if you turn off the stochasticity, this state actually died. All right. Thank you for your attention, and these are the reference. 2 is still in press in the final revision with the editor. And if you're interested in the physical this physical motivated symptomatic analysis, and we published it in Journal of Stat Phys last year. Thank you, and I'll take questions now.
We have time for a couple of questions. Any questions? So, can you elaborate on the difference between so-called passive dispersal and active dispersal, please?
Yes. So the passive dispersal actually are used by actually a lot of physicists. Actually, when they do this business, they use passive dispersal. So in the passive dispersal, what you see is the per capita rate of movement. So the per capita rate of movement is just some constant. So usually in this ODE system, what you see is like dN dt, 1 over n